First, I would like to thank the organizer for the kind invitation and for putting together this interesting event. So today, I'm very glad to be here to speak about my research. So this is a joint work with Habib Amari from UTH at Zurich. So here is the outline of my talk. I will first basically introduce some basic background of super resolution, and then I will talk about two examples where super resolution can be realized by using subwavelength resonators. The two examples are Helmholtz resonators and air bubbles. So finally, I don't think I have time to go through the third part, which is about the plasmonic sensing. So we know that the resolution is a very fundamental concept in imaging science. So in optical microscopy, so we know that a point source can produce diffraction patterns on the imaging plane. So this diffraction pattern has a very bright spot in the center, which is called the airy disk, and the range of much weaker brightness. So if two sources are very far away from each other, their airy disk don't overlap, and we can tell from their different pattern that we have two sources. So if two sources are very close, their airy disks overlap, and we cannot tell from this different pattern whether we have one sources or two sources. So in this case, the two sources are not resolved. So resolution is defined to be the minimum distance between two sources that can be resolved by a microscopy. So this also tells us that the resolution is actually determined by the diameter of the airy disk. So in physics, we know that the airy disk is formed by focusing the light from the far field onto the imaging plane. So Abby did cover that there's a fundamental limit on the size of the focus spot. So this limit is given by half of the wavelength of the waves emitted from the source. So as a result, we can see that the resolution limit is actually equal to the half of the wavelength of the wave emitted from the sources. So there's another way to view this diffraction resolution limit. So if you look at the field produced by the point sources, so this field can be decomposed into two parts. So the first part is propagating modes, which can propagate away from the source and into the far field. So this propagating modes can be measured, but they only carry information about the sources on the scale which is greater than the wavelength of the waves. The other part is evolution modes. So these modes, they cannot propagate to the far field, they cannot be measured, but they carry information about the sources on the scale smaller than the wavelength. So as a result, we see that the resolution is actually limited by this wavelength. So this analysis is very well known in the homogeneous space, so where we can have Fourier analysis, Fourier optics, and we can define the wavelengths. So however, if we are in inhomogeneous space, then the wavelength is not a well-defined concept. So as a result, we have to recast this problem as an inverse source problem. So now we have an inhomogeneous space, which is characterized by the refractive index n, and we have sources scattered inside this domain. So the field emitted by these sources is given by this forward operator, so which is basically the convolution of the Green's function for this medium and the source distribution. So the inverse source problem is to reconstruct the source distribution f from the far field data u. So time reversal method is very popular to solve this inverse source problem. So it's very simple. We just apply the adjoint operator of the forward operator to the measurement, and we form an image. So in addition to this time reversal method, we have a lot of optimization-based approach. So here is the remark. So actually, the time reversal method is a direct imaging method without assuming any a priori information about the sources. For the optimization-based approach, we have to use a priori information. So actually, the time reversal is in close relation to the focusing step in the microscopy, where the image is formed. So if we work with this the joint operator closely, we can see that the imaging functional is actually given by this formula. So which is the convolution of the imaginary part of the gradient function for the medium and the source distribution. So if we take this f to be a pointer source, and we obtain the point spread function of the imaging function, which is given by the imaginary part of the gradient function. So the result from here, we can conclude that the resolution of time reversal method is determined by the imaginary part of gradient function. This varies from location to location, and this is also the resolution limit for the inverse source problem without any a priori information. So this can also be viewed as an generalization for the Abbe diversion limit. So this resolution limit, or the minimum separation between these sources, actually play a very important role when we solve the inverse source problem. Actually, this separation, minimum separation determines the well-posedness or the stability of the inverse source problem. So it's we have the very nice result given by Candace and Fernando, which show that for the observation-based approach to work, the sources need to be well separated. Means that the separation distance must be greater than the wavelength. So there are many super resolution techniques. So more than about 100 years ago, so CICS proposed the idea of near-field scanning optical microscopy, which utilize the near field, which carry high spatial information of the sources to realize super resolution. And also we have the Nobel Prize winning works, so which use thousands of images to produce a single high resolution image. And also we have this structured illumination method. But here in my talk, I want to focus on a particular technique which was inspired by the recent advance in the field of metamaterial. So Pendry first proposes the idea of perfect lens, which you can realize perfect imaging. And also I think the president of this university, Zhang, he also proposed the idea of using superlens, hyperlens. So this, so mathematically speaking, so this the mechanism of this perfect lens can be explained by the nucleized anomalous resonance, which was discovered by Graham Milton 10 years ago, before the work by Pendry. And in my work, I want to focus on the other approach proposed by Mathieu Fink's group in France. So they proposed the idea of using resonant media, which consists of subwavelength resonators. So the idea of this approach is to encode the near-field information of the sources to resonant modes of the resonators, so we can propagate into the far field. So I will show two examples to demonstrate this idea. So the first example is about the Helmholtz resonators. So Helmholtz resonator is acoustic cavity, so it has a very big volume and a very small opening. So the main property of this Helmholtz resonator is that when the incident wave has frequency close to the resonant frequency, then the scattering is much enhanced. So actually, we can show that there is no frequency resonance, which is proportional to the square root of epsilon. So epsilon is the size of these openings. So because of this result, so Helmholtz resonator is a sub-wavelength resonator, because this is a low-frequency resonance. The wavelength is much greater than the size of the resonator. So using these Helmholtz resonators, this group of scientists in France, they performed a very exciting experiment, superfocusing experiment. So this is the setup of their experiment. So we have a pointer. So this is a time reversal experiment. In the first step, so the pointer source above these cocoa cans emit a pulse. So this pulse is scattered by these cocoa cans, and the scattered wave propagates into the far field, and they are recorded. In the second step, the recorded signal is time reversal, and then it emitted through these speakers to this medium to form a focus spot at the location where the source locates. So they measure the focus spot, and they found that the focus spot has the size about 0.1 meter. And then they do the same experiment without these cocoa cans. They found that the focus spot has a size about 1 meter, so which is 10 times of the spots with the presence of cocoa cans. So the 1 meter is actually the diffraction limit, which was dictated by the physics. So they call, because of this reason, they call this super focusing. And this super focusing actually implies super resolution, because if we perform time reversal imaging in this medium, then we can achieve super resolution. So I'm very interested in this experiment. So I try to explain this by using mathematics. So actually, the physics can be modeled by this time domain scattering problem. So we have a pointer source, and the pointer source emits a signal ft, and we have a Newman boundary conditions. And we can work out that the focused field from the time reversal experiment actually is given by this formula. So where this is the integral of the modulated imaginary part of Green function, which the signal emitted by the source. So in order to understand the super focusing, we have to analyze this asymptotic for the Green function. So actually, using asymptotic analysis, we can show that this Green function has this asymptotic form. So this consists of several parts. So the first part is the Green function in the space without resonators. So this is diffraction limit term. So there's no use here, and also some other small terms. And there's a very special term here. So this term actually given by the resonant modes of these resonators. So actually, you can show that we can see that when the frequency, is close to these resonant frequencies, then these resonant modes will be amplified. So, and we can also show that these resonant modes, they are subwavelengths, and they depend on the relative position of the source to the cavity apertures. So using the asymptotic of the Green function, we can show that the focused field actually has this asymptotic expansion. So the first term is diffraction limit, is not interesting. So the second term is actually given by the contribution of these resonant modes. So this x naught is the source location. X is the place where we measure the field, and this zj are the locations of the resonators. So we draw the graph for this term, which was induced by the resonance, and we found that indeed super focusing can be realized. So here we did some numericals, and so the source is located at this point, and which is about 0.2 above the cocoa cans. And if we do the experiment, we see that this is the focused spot, which is of order 1. So, and this is the field distribution. So without the cocoa can, without the resonators, we see that the focused spot will occupy all this square domain. So there's no hope for super resolution. So this demonstrates that indeed using this resonance, super focusing can be achieved. So now let's come to another example. So air bubbles. So air bubble is a very interesting acoustic materials. So it has a very high contrast in the density of airs and the density of water. So we see that the density of air is actually 1,000 times lighter than the density of the water, and also the air is 1,000 times easier compressible than the water. So the result, we have very high contrast between the density of the medium inside the bubble and outside, and also between the Bock modulus inside and outside. However, on the other hand, if you look at the wave speed or the wave number inside the bubble and outside the bubble, so they don't differ too much. So the contrast is on the same scale. However, we have a big contrast in the density and the Bock modulus. So because of this high contrast, so bubbles have a very interesting acoustical properties. So actually, Venus was the first to discover that there is a quasi-static resonance for these bubbles. So we call this Venus resonance. So here we have found a formula for this Venus resonance, so which is proportional to square root of delta. So delta is the contrast between the air density and the density of the water. So so this formula shows that these air bubbles are indeed ideal sub-wavelength resonators for acoustical waves. So using this fact, so this group of scientists in Paris, they formed a superfocusing experiment by using this air bubble. So in a water tank, they generate a lot of bubbles, and then they do this time reverse experiment, and then they realize a superfocusing, so where the focus spot is much smaller than the focus spot without air bubbles. So this is a superfocusing experiment. So I'm also very interested in the mechanism, mathematical explanation behind this experiment. So my way to do this is that I form this as a scattering problem. So I assume that I have a large number n of identical bubbles, and then I have incident plane wave, and then I look at the scattered wave, and then I try to understand when the number of bubbles tend to infinity, what do we get? So basically, I want to develop an effective medium theory for this bubbling medium. So this is the result I obtained. Actually, I can show that under some assumptions, which are technical assumptions. So we can show that the microscopic field UN converges to a macroscopic field U. So here is the effective parameter V. It's very interesting if you look at the form, if you look at the expressions. So this lambda is related to the volume fraction of the bubbles, and this V tilde is related to the normalized density of the bubble centers. And the interesting part is on this frequency dependent part. So this omega m is the Venus resonance, and this omega is the frequency. So it's very clear that when omega is below this Venus resonance frequency, so we have a positive number here. So then this V is positive, and if omega is only slightly below this one, then this number can be very large, and then we have a very big V, and then we have a very high refractive index effective medium. And then I will show in the next step that this actually implies superfocusing. So on the other hand, if this frequency is above this Venus resonance frequency, then this number is negative, then this V is negative, and then we get an effective negative Buckle modulus. Then in that medium, the wave cannot propagate. We have diffusion phenomenon. And also, on the other hand, if this frequency is right at this Venus resonance frequency, we can show that there's no effective medium. So now I will show that this high refractive index actually implies superfocusing. So the idea is to develop a resonant expansion for the gradient function in this high refractive index medium. So actually, we can show that this gradient function consists of the gradient function in the free space and the resonant modes. So when the contrast is very high, we can show that sub-wavelength resonant modes can be excited, and this can contribute to the super resolution or super focusing. And this is indeed the case. We did some experiments. So here we have a high contrast media, so which occupies a domain, which occupies a disk of radius 2. And we have a low frequency wave incoming, so the wave number is fixed to be 1 outside this high contrast medium. And then we draw so we vary the contrast of the medium. We draw this scattering diagram. So this horizontal line represents the contrast in this medium, and this vertical line represents the total scattering cross section. So this measures how strong the scattering is. Using this scattering diagram, we can pick up the resonance. So basically, at these peaks, we can have resonance. And at the valleys, we don't have resonance. And we draw the corresponding gradient function at the resonance frequencies. And we show that when resonance occurs, we have very highly oscillatory imaginary arc of gradient function. So this actually implies this gives us subwavelength structures, and this can give us super resolution. So on the other hand, this vanishes, so there's no resonance. We draw the same picture for the Green function. We notice that the Green function is almost flat. So there's no subwavelength resonant modes. So there's no way to obtain super focusing or super resolution. So actually, this gives us a very conclusive results that super focusing is due to the sub-wavelength resonant modes excited by this high contrast medium. It's not simply because of high contrast medium. It's because of the resonant modes. Okay, so far I think I have talked about this. Give you a quick review. I talk about the super resolution is due to this near field interactions of the source with resonant media, which can encode the near field information of the source into the sub-wavelength resonant modes of the resonators we can pop into the far field. And this idea actually can trace back to the central idea, which was about 100 years ago. So, and actually I think this idea can go beyond this super focusing. So actually we can talk about sensing. So, but I think I should stop here because this is it's already very late. I don't want to ruin your evening. So I will stop here. Thank you very much for your attention. In the optical imaging, yes, we need. In that case, we can use some resonant media. For example, there's some optical resonators like plasmonic particles. So okay, let me give you some idea what we did here. So here we can do this. Actually, do some sensing. So we have a very small particle, very small, so that there's a very few scattering, and then we can put a sensor, optical sensor, which is a plasmonic resonant particle close to it. And then because of the presence of this small particle, the resonant frequency of the particle will be shifted. And we can measure the shift from the far field. And from this shift, actually we can recover some information about these small particles. So this, we have to use some resonant effect to enhance the signal. Yes.
Okay, no more questions at the end of this afternoon session, and thank you all for staying late with us, and have a good evening.